we've got three speakers. There's a lot of folks in the community that probably could have provided some useful stuff, and I hope folks online who do high resolution modeling in the Arctic will join the conversation as we get into some of the discussion after the presentations. But we've lined up three folks to sort of introduce the topic of how high resolution simulation in the Arctic impacts things in terms of the processes that are simulated, whether they be in any one of the component models or in coupling between models. But there are certainly a lot of things where high resolution gives you different answers for a variety of reasons. And so the folks we have lined up today are Eric Chassignet from Florida State University, who's been doing some high resolution modeling using HICOM. Stephen Kabbalah from University of Oklahoma, who's been doing some atmospheric modeling at high resolution, is going to talk about some of the issues related to that. And Wisław Mysłowski from the Naval Postgraduate School, who's been running a variety of resolutions of system models in the Arctic, and is going to talk a little bit about some of the processes that are represented or not represented in different resolutions. So we're going to try and keep it to about 10 to 12 minutes per presentation as we go through those three folks, and then open it up to a more wide range of discussion from other folks on the phone. So if you have questions of clarification, please go ahead and jump in or raise your hand online, and we'll get those answered maybe during the presentations. But I would like to get the full perspective from those three folks, and then we'll kind of open it up and have a longer discussion about the role of resolution in Arctic modeling after that. So with that, I don't want to take too much time, so we can try and stay on schedule. And I think first up is going to be Eric Chassignet. Is that correct, Emily?
It is. Yep.
Okay. And are you going to run it there so we can see it on the screen?
Actually, Eric is going to share his own slides.
Okay. Great.
Right, but suddenly the window disappeared. What happened there? Okay, I see you guys, but I don't see the.
When you hover.
Okay, I got it.
See, yeah, there you go.
Thank you.
No, you're fine.
It was minimized for some reason.
Yeah, it disappears sometimes.
Okay, so can you see the screen now?
Yes, we can. Looks good.
Okay, so I'm here with Dimitri Dukovskoy, who has been doing most of the work with the HICOM Arctic configuration. And first, like to do one quick remark on some of the work that we did in the Atlantic, North Atlantic. And going to 1/50th a degree, which is about 1.5 kilometers at mid-latitude, we got a significant improvement in the Gulf Stream model representation as the resolutions increased from 1/8 degree to 1/50th degree. And why it's important is because the Rossby deformation is about 40 kilometers, and even truly resolving the sub-mesoscale has an impact on the Gulf Stream path and recirculation. So just very briefly, 2 minutes. On the left, top left, is the observations based on a collection of hydrographic data and drifters and so on. And on the right is the 1/50th degree, and you see that you have a good match. But when you go to the 1/12, the Gulf Stream does not penetrate very far in the interior, and 1/25, the recirculation does not really pass the New England Seamounts, and the recirculation is also very intense south of it. So the big difference, this is the relative vorticity in winter at 1/12 degree. If I go to the 1/25, you see back and forth at 1/50th, you see the emergence of a large amount of very, very small scale structures. And the size of middle scale feature is a function of mixed layer depths. It's due to the mixed layer instability. And you can only resolve it when you get to the 1.5 kilometer grid that we have there. So that has also a profound impact on power spectra, many things there, but also if you look at the eddy kinetic energy, you have a good representation in 1/50th compared to the observations. The IVSO in this case looks that it's less energetic, but it's due to the fact the way it's been sampled. And if you look at a section of 55 West, the biggest thing is you see the penetration of the EKE, the eddy kinetic energy, into the interior now resemble the observation, whereas both the 1/12 degree and the 1/25 does not. So just to show that, at mid-latitude, high resolution really matters. So, there is expectation that in the Arctic, it's also going to matter because the Rossby reduced deformation is much smaller. So here's a little bit of a list of why we need high resolution in the ocean. First, we need to accurately represent the Western Banner Current, the East Greenland Current, and the West Pittsburgh. River plume dynamics and coastal river regions, many small-scale eddies, ocean fronts, and especially flow and ice transport through narrow straits. You have a lot of narrow straits in the Arctic. So here is just a review of why the Rossby Reduced Formation is very small. I mean, in the interior, which is circled, the red circle, you have about order about 15 kilometers. If you go on the shelf, which are the purple, this one and this one here, it's quite small. It's 4 kilometers. And if you are into the subpolar North Atlantic, it's about 8 kilometers. Now, in order for a numerical model to truly resolve those those features, I mean, the eddies that are formed through outline instability, you need to have about 4 to 6 grid points per eddy. So it means that over the Arctic shelf, at a minimum, you need a grid spacing about in the order of 1 kilometer, 4 kilometers for the Arctic interior, and for the subpolar North Atlantic, about 2 kilometers. So here is some work that Dimitri and several of us did, is to compare the impact of resolution in 3 different models. On the left is the Arctic Ocean HICOM that Dimitri ran, the NEMO Link 2, which is European, and the ICC MMG. Sorry, yeah.
NEMO Link 2 is Canadian.
Oh, it's a Canadian version, not the. Okay, thank you. So the main point in here is you see this is a freshwater propagation in there, and you see that all this big red area is that the coarse resolution is not able to maintain the trapping of the coastal boundary current around the Greenland coast, and therefore you have excessive advection of the tracer into the interior ocean. Now, the other location to look at is in this right here into the interior Labrador and Maguro, the Nordic seas. You have almost no propagation in the coarse resolution, and that's due to the fact that the eddies are not able to take away the fresh water from the boundary current into the interior, and that's done better as you increase the resolution. One way to look at this is to look at the eddy fluxes of Greenland freshwater inside the model, and if we look at the contribution to the interior Labrador seas, in blue, the blue lines here corresponds to the mean eddy flux, the average U average C that here on the top, and the eddy fluxes are represented in red on the right-hand side. And you can see that at half a degree or a quarter degree, the eddy fluxes are pretty much non-existent, 0. And when you go to high resolution, which is about, so I forgot to mention, it's about 4 kilometers on average for the HICOM, 12 kilometers for the NEMO Lim, and about 20 kilometers for the ICMMG. And so the eddy flux becomes comparable to the mean flux. So what we have done is also perform identical series of experiments with varying resolution. We had a coarse resolution at 3/4 degree that served our base experiment. But mostly what we have done, focus a lot, several experiments at the 1/12 degree. That's our workhorse. And more recently, Dimitri has configured the Arctic Ocean to 1/25 degree or 0.04 degree, about 2 kilometers, and designed to be compared to the 0.08. Our dream is to go to 1/50 degree, but that's extremely demanding on computer time and storage, and we'll see if we can get to that point. So a few slides to illustrate the differences here. Classic one is to look at the relative vorticity, ratio of the relative vorticity to F. And on the right-hand side is a 1/12 degree, and you see a fair amount of eddy activity, but that is significantly enhanced as you double the resolution. And the main thing is you see many more eddies in the interior here in the Labrador Sea and everything. And that translates into the flux, of Greenland freshwater, and that's a tracer that mimics the freshwater transport here. You see that in the 1/12 degree, it remains in the western boundary current. It's not advected in the interior when you go to the 0.04 or the 1/25th of a degree. Another way to look at this is those, again, on the right is the 1/12th degree, 1/25th on the left. And that's the temperature that you see. And what's important to look, if you look at the end of the white arrow, there you have extremely small scale structure. Like here, you have little mushroom filaments here, very small eddies, and here you have eddies are formed along the boundary current. And so that is not present in the 1/12th degree. And that's very important because we do need that resolution for an accurate representation of all the dynamic processes that are taking place in the coastal regions. And that's based on the paper by Karnak et al. And all along this, the red lines are here, precisely here. So in order to accurately represent the mechanisms that affect the buoyancy driven flow in the Arctic, like some of the eddies formed along the shelf and due to the river outflow, resolution is needed. And that's what we start to see in here, that you can start to see that some of the features are well represented. Another aspect that is very important, here we take one example. It's just how well the straits are represented. There are many, many straits in the Arctic Ocean that do matter. So we take one example, the Bering Strait, which is only 85 kilometer wide and 50 meter deep. It's the conduit, of course, between the Pacific and the Arctic, but it's one of the major freshwater source as well as nutrient source. And so you have very distinct temperature and salinity gradient that goes through the Bering Strait. And here's an example from our 3/4 degree simulation that has only 4 grid points. And in this case, on the left are the observations for the months of August 2010. You see that you have a very strong gradient in temperature from the left to the right, as well in the salinity. Absolutely not represented when you're in coarse resolution. 1/12th degree, you start to have a structure that is resembles more closely the observations, but you're lacking a lot of the fine structure, especially some of the freshwater input here. In the salinity that you see on the right. So major improvement as you increase resolution. It's at about 20 grid points, but many of those straits are smaller and need to be represented. So in brief, that's some of the points that we wanted to bring up, and we can, Dimitri is here with me and can answer later on also some very specific questions that you may have.
Great. Does anyone have any questions? Just brief questions for Eric and Dimitri?
Hi, this is Jeff T. Can you hear me?
Yes, we can.
Yes, Eric, I have a quick question. So when you run your 1/50th degree, what kind of computer you're running?
Oh, we use the ONR DoD computers.
And then if you do a 1-year simulation, how long does it take?
It's about 500,000 CPU hours per year. So it's fairly demanding.
Yeah, thank you.
Eric? Yes, this is Wilbert Dwyer. Thanks. It was a really interesting presentation. So, of course, the spatial resolution is very important to get the boundary currents right and all that kind of stuff. But if you go to the Arctic, do you have really a sense of how important eddies really are? I mean, on mid-latitudes, if eddies are 10 kilometers or maybe 30 kilometers, you can really imagine that they have a big potential to mix over long distances. But if you are in the Arctic and have eddies of about a kilometer or so, how effective, how important are they really for transporting water mass properties or stuff like that, mixing basically?
So I can jump in. Yeah, this is a good question. We found that the eddies are very important for the North Atlantic, especially for the Labrador Sea. And as you probably saw in the slides that Eric just showed, the difference in the freshwater transport between different models of different resolution is drastically different. And even between the HICAM, the same model, but with the 004 and 008, the freshwater transport from, it was tracer transport in the two simulations is different. Yeah, this picture. Yeah, this one. You see in the 008, the Labrador current still has a relatively high concentration of the tracers. And this is probably because the mixing is, the eddy flux of the tracer is much weaker in the 008 model compared to 004. In the Arctic Ocean, especially in winter, what I see in the simulation, the eddy flux is not that critical, but it becomes critical during the summer when under the ice-free conditions. So when the dynamics becomes more rapid, more intensified, mostly due to the stronger wind stresses.
Mm-hmm. Okay, thanks.
Okay, thanks. Let's hold any other questions and go to our next speaker, Stephen Cavallo from University of Oklahoma, for some atmospheric perspective.
All right. Can everyone hear me?
Yep.
Everyone see. All right. Well, thanks for taking the time to listen to me talk today. So this is work, thanks to NSF and ONR. And so I've listed so Bill Scamrock with the ONR and a couple of grad students, one with the ONR project and one on the NSF side. So let's see. There we go. Just trying to. So on the forecast skill in the Arctic plot here, what we see here is that the Arctic forecasts in the mean sense aren't really that much worse in 5-day forecast from ECMWF, which is measured here in terms of the anomaly correlation coefficient. So 1 is perfect, 0.6 is any kind of skill whatsoever, and 0.8 is what the desirable skill should be for, I guess, a decent skill. And so if you compare, for instance, going back to 2008 through 2016, the Northern Hemisphere, which is shaded in this red tint, versus the Arctic, you can see that and these are the 99th and 1st percentiles. Even though the mean scores are just slightly lower in the Arctic, there's a lot more bad forecasts in the Arctic. And so there's some really bad forecasts in the Arctic, and this is annually. In the summer, I think that's particularly stronger, even that you get these really bad forecasts that drop below 0.6, so no skill whatsoever.
Sorry for the interruption, but we're not seeing your slides.
Yeah, we're still on that first slide, Stephen.
Okay.
It hasn't.
So let's see. I don't know what to hit
So
here.
I am saving your presentation right now. If it's not working, let's see. Do you want me to try to share the slides for you?
Well, let's see. So should I retry or whatever works, I guess? Well, I just tell you to switch to the next one then?
Yeah, so, yep, we'll try that.
Yeah. Maybe that is best.
So is this showing up on your screen?
Yeah, so if you could hit view full screen, that'll get rid of all the other tabs.
Full screen.
All right.
So are you looking at the second slide now?
Yeah, so the one that says forecast skill in the Arctic. So I guess you won't be able to see my cursor now, but so what I was showing on this plot, I started on this top left, and so the forecast skill in the Arctic as a whole, on the mean sense, is just a little bit lower than the Northern Hemisphere, which is the red is the Northern Hemisphere, blue is the Arctic. And these are 5-day forecasts from ECMWF. But the range of forecast skill is a lot larger for the Arctic. So you get a lot. And so especially for these lower skill scores down here around 0.7, 0.6, there's a lot more really bad forecasts in the Arctic, and those are in 5 days only. If you extend that out on the right to a 30-day forecast, and this is from Young et al., you can see what this is showing is that in the extended range, the Arctic really matters. So the black is a control ECMWF 30-day forecast, and if you nudge you repeat that experiment but nudge the Arctic areas north of 70 degrees north latitude to the reanalysis, you reduce your root mean square error quite considerably. In fact, more than in the tropics, which is the red, or more than in just part of the Arctic. And so it's, what this is showing is that the global forecasts and the extended range are very sensitive to what's happening in the Arctic, but we don't know why. And so key polar processes have not been identified. If you could go to the next slide. Whoops, I think we skipped one. Or is this it? So what time scales matter in the Arctic? And so on the left here, this is the power spectrum of the CESM, the large ensemble is a function. So you're seeing period and days here. And each of these different lines is just a different period in the integration here. And so at the short time scales, there's not really much difference. You can't really discern any difference. But at the larger time scales, you see that in the projections of future climate, there's going to be difference in sea ice variability, for instance. So can we really believe that there is no change here at the short time scales? So if we take a look at that in more detail and plot the observed sea ice variability from NSIDC sea ice extent and compare that to the CESM climate model, you see it's about an order of magnitude more power in the observations at the short to extended ranges. So up to about 30 days, 20 days or less, there's a big difference. And so that suggests that there is variability at the weather time scales that's not being accounted for, and that we might not be accounting for that in climate projections. Next slide, please. So I think it's pretty well known that sea ice is hard to predict. This is from Hamilton and Strovey about the search sea ice outlook forecasts. So there's a lot of forecast 37 forecast method, 101 forecasts from 2015. The gray shading is the interquartile range of those forecasts. And so some of them are dynamical models, some of them are statistical, some of them are quasi-operational, the pretty good models. And it does not correlate with this red, which is the observed sea ice extent in September. So there's very little skill, which they say is perhaps attributed to atmospheric conditions at short timescales. So the next slide. So then the question is, do the short-term processes have an impact on things that are very characteristic of the Arctic, like sea ice? And so for instance, we know that there's upper tropospheric disturbances and they induce surface cyclones. Surface cyclones exert strong surface wind if they're strong enough, and we've seen some strong cyclones lately in the Arctic. And ice is also thinning, and if you have more open water, more recent studies have shown that the increased fetch can have an effect on the wave amplitude and ice fracturing, causing some pretty rapid ice loss, sort of a positive feedback. And here's an example of 2006, a cyclone here shown in blue on the left plot, just northeast of the tip of Greenland. And then right at that same location and satellite on the right, you can see a hole in the sea ice, and that's just from one cyclone. Next slide. And so one issue in the Arctic is, which Eric had actually talked about for the ocean, and the same thing in the atmosphere, the Rossby radius of deformation is much smaller. And so we're used to, in the mid-latitudes, atmospheric scales for cyclones are around 1,000 kilometers, but that's about half in the Arctic, and especially as you get further north. This is due to the effects of the Earth's rotation. And so you can't get away with the same resolution necessarily that you can get away with in the mid-latitudes. So for instance, if we're trying to resolve a cyclone in the mid-latitudes, we're trying to resolve something at 1,000 kilometers, and it's about half that in the Arctic. So examples of things that have very small scale or polar lows. And then I'm going to talk about Arctic cyclones and these upper tropospheric disturbances called Tropopause polar vortices coming up. So next slide. So Tropopause polar vortices are these upper level precursors to surface cyclones. And surface cyclones, as we saw, as I talked about before, there can be some pretty bad forecast skills. So predictability perhaps poor. and at the same time, they might be important for some of that short to extended range variability in the atmosphere and perhaps on sea ice. But yet weak TPVs are there sometimes for months before the formation of a surface cyclone, yet we can't predict that. And so here's an example of their scale. On the left is 500 millibar heights. This green arrow circumnavigating the pole is the polar jet stream, which bounds the tropospheric polar vortex. It's actually within the polar vortex that you have these smaller scale features. The blue spots that are circled are the Tropopause polar vortices. And you can have a lot at any given time. On the plot on the right is a flattened version of a snapshot centered at the North Pole. And you can see that there's a lot of these vortices at any given time, a lot of the Tropopause polar vortices, but also because of the effects of the Rossby radius, the atmospheric dynamics is different. It's just inherently different between the mid-latitudes and the tropics. So in the mid-latitudes and the tropics, you have more wavy features, and so waves tend to dominate the flow. But once you get towards the Arctic, because of the rotation effect, the atmosphere favors vortices, and so these are the Tropopause polar vortices. And so the vortices dominate in high latitudes, which is more of a nonlinear problem. If we go to the next slide. The physics is also different. So the physical processes are dominated by radiation and water vapor. And this plot on the left shows where it's blue is where radiation, on average, the effects of radiation are greater than the effects of latent heating. Everywhere where it's red, so that's pretty much most of the globe, is where latent heating is more important in the net sense than radiation. And so that's unique about the Arctic, is that it's radiation that runs the physics. There is latent heating as well, but radiation is more dominant than in the mid-latitudes or tropics especially. And so on the right is an experiment so the question is how much of the TPV evolution is dominated by radiation and by water vapor. And so this solid black line shows the effects of TPV strengthening without water vapor versus the dashed black line with water vapor. And the dashed black line is more of what we think is observed. So the water vapor is really important in relation to radiation, because these features are located at the upper troposphere, lower stratosphere, where pretty much water vapor it's low, but it's high enough to have a strong impact on radiation, but yet ozone isn't high enough to have much of an impact on radiation. And since radiation is running the show up there, it really comes down to how things are being impacted by water vapor at that level. So next slide. So this has motivated us to develop so we think we need global coupled non-hydrostatic modeling. And so we have been working on MPAS, which is the model for the prediction across scales, and coupling that with the climate models that was referred to earlier, CESM. And the nice features about MPAS are the fact that it's a global model, and so we don't have to worry about boundary conditions. So in atmospheric modeling, boundary conditions can cause issues, a lot of issues with wave reflection especially. And so we get rid of this if we have a global model. And the fact that we have this refinement of the grid. So if you look real close, these are all grid cells. They're close together right over the Arctic, and they're further apart away from that. And that's just by the way we designed our mesh. We can choose that higher resolution to be anywhere. And so we can have a global model with high resolution in the areas of interest without having an unreasonably computationally expensive simulation. And we can also account for the couplings that are important, for instance, with sea ice, and sea ice is so variable in the Arctic. Next slide. So here's an example of what this effect is. Having the variable resolution is the plot on the left, and this is of vorticity in the middle troposphere under a 5-day forecast versus just a uniform mesh on the right. And so, for instance, these vortices, TPVs, which we think are important for surface cyclones, are much better. There's a much more structure that's very apparent. And this is that exact case that I showed you earlier where the sea ice was opening up from that cyclone in 2006. So you see a lot more structure because of the higher resolution, which we think is important, especially since it's feeding back the sea ice and water vapor. And then the uniform one on the right. Next slide. And here's again those observations on the left panel earlier. And this is our forecast now of that 5 days, a 5-day forecast from MPAS CESM, showing that indeed, at least in the model, we're getting that there is a big impact from the surface cyclone on the sea ice. And in the model, that sea ice hole does come from that surface cyclone. And this TPV was actually present. This was an 86-day Tropopause polar vortex. And so it was present long before the formation of that surface cyclone. Next slide. So we've looked at the sensitivity to varying the mesh and the physics. And so these are tracks of that 2006 TPV. So the forecast lead time is on the y-axis, and the track error is on the x-axis. And from our ensemble that we designed, varying the resolution. So on the right, we see the control, which is a uniform 30-kilometer mesh. The middle one is the Arctic, where we've refined the mesh to be highest resolution over the Arctic. And the right one is the inverse of that problem, where we've refined the mesh to be highest over the mid-latitudes and lowest over the Arctic. And in an experiment, hypothesizing that perhaps it's Rossby wave activity or mid-latitude convection that's most important to what ends up happening in the Arctic. So it ends up that this Arctic one, the one in the middle, performs the best. And so this is that blue line. So we're right around 9 to 10 days on the left plot. The tracks diverge, but the best ones best forecasts seem to come from when we have the Arctic higher resolution mesh. So the next slide. So we've been testing this out on more and more cases. And so we've actually been testing this out now on sea ice predictions for, so subseasonal to seasonal predictions. So for instance, summer of 2012 was an interesting case because there was an apparent, a strong cyclone that apparently had a large impact on the record low sea ice extent of that year. And so weather processes were likely important. And so this is what happens on the left plot, is showing the observations from NSIDC in the black, and then the MPAS CESM, which is our system here in blue, which we initialized from the CESM large ensemble. And so if we just run that CESM large ensemble out, we get pretty big bias in the sea ice extent a month or so later. In the MPAS CESM, our forecast, we see some of the, so even though we still have a lot of error, we started out with pretty large initial condition bias. And so we couldn't, this is something that we can't really fix. When I'm gonna bring that up at the very end, it is an issue, a remaining issue that I think is crucial. But we get the right trend, and we get to this dip here on September 1st, 2012, was that we were getting a strong cyclone in our simulation. So even though it's not happening at the exact right times, we tend to get the right, if we start out with the right pattern in the atmosphere and the right sea ice pattern, we tend to get the right cyclone structure, which then feeds back to the sea ice more correctly. And we ended up with not too bad of a forecast. And so that was sort of in the middle of these search sea ice forecasts for 2012. Next slide. We repeated this again for 2017, this year, and got an even better forecast. We actually came in second place of all of the dynamical models, which there were 14 of. And so that includes GFDL. I think number 1 was NASA. And so our forecast, we're now doing ensemble forecasts of that. And so our forecast is a solid blue line. And so it really comes close to the observed sea ice extent. We have some issues still remaining, of course, at about 2-month forecast with the timing of the sea ice minimum. But overall, we get the right trend leading up to that. And interestingly, these dashed blue lines are if we initialize with just slightly different atmospheric initial conditions, slightly coarser, I should say. These are all the dashed ones are coarser initializations of the atmosphere. We get trajectories that are substantially different. And so our forecast on the right here, this is the number of forecasts that are submitted to this search sea ice outlook. And the black line is what was observed, we were pretty much one of the closest, we were the second closest dynamical model, one of the closest overall models here for that. And so we're still working on that. And so there's still, obviously, if you look back on the left, we have that same problem where our initial conditions start out fairly different from reality. And that's, I think, a data assimilation issue. Next slide. So just to sum it up, so I'm just gonna leave some of this up here and not go through every little point here. But I think if I move to this bottom point, I wanted to talk about where we think we should go with this. So we think the high resolution atmosphere is crucially important in order to get the right representation of these cyclones because of the tropopause polar vortices. So they're small scales. And so Eric actually talked about to the effective resolution. And in the atmosphere, I think, and Eric was saying in the ocean, it was 4 to 6 delta X, but in the atmosphere, with our model, it's actually 7 delta X. So we need that high resolution because if it comes down to water vapor, the structure of water vapor really matters on the evolution of these tropopause polar vortices. But we also need to be able to account for how it feeds back with sea ice and how that feeds back up into the atmosphere. And so we think TPVs are located in the most data sparse region of the Arctic for what we want to observe of them. We want to observe the water vapor at the upper troposphere and lower stratosphere, but we don't really have any reliable water vapor measurements. There's a lot of uncertainty in the observations that do come in from that, and the uncertainty apparently is high enough. We have a very systematic bias in forecasts of the intensity of tropopause polar vortices. And so if we're consistently underestimating the strength, which means we're also consistently underestimating the strength of Arctic cyclones. And so that means that we're also perhaps misestimating how much the sea ice is going to evolve because of that. And so we really need to have some targeted observation campaigns in order to fix. We don't know exactly where things are wrong in the model, and we can't figure that out unless we go and take some good detailed observations of tropopause polar vortices. But as you saw too on those slides when we were doing the seasonal forecast of sea ice, we have an initial condition bias. So we really need to think about data assimilation. We think that's crucially needed in order, so we have the right trajectory. If only we could just get rid of that initial condition bias, then perhaps we would actually have really good forecasts. Another benefit of data assimilation too is that it helps us assess where the model bias is as well. And so we're looking to move forward on those two aspects. We think those are the most important things to look at in the future. So that's it, and I'm happy to take any questions. Thanks for your time.
Okay, thanks, Stephen. If there's no pressing, I know there's already some questions online, but let's go ahead and move to Vislav's presentation, and then try to handle all the questions in the discussion periods left, because I'd like to get the third presentation in before we start diving into some more of this discussion about high resolution impact on predictability and data assimilation. There's all great topics. I know we're just scratching the surface on all this, but let's switch to Vislav and go through that presentation with another system model, and then we'll have an open discussion where we can address some of these questions that have already popped up.
Okay, can you hear me and see the screen?
Yes, we can.
Okay. Is this a full screen mode now?
Yes, it is. Looks good.
Okay, so this is a presentation actually very well introduced by the previous two speakers, because we're covering the ocean and the atmosphere as well as the sea ice and the land hydrology here. We're using a regional Arctic system model to look at the importance of various processes, coupling among different components, and how we can improve the modeling as well as prediction of the Arctic states, both sea ice, but also climate in general. I wanted to emphasize that this project has been complementary supported by ONR and DOE, and also we have some support from National Science Foundation, both for the marine biogeochemistry modeling as well as the cyclone investigations as well. And I'm not going to read all the names here, but you have the PowerPoint slides so you can see who is involved in this project. So basically, briefly, a rationale is that, as previous speakers mentioned, some of the changes in the Arctic, or basically on the Earth, are happening in the Arctic, and in particular related to sea ice. The rate of Arctic climate change predicted and simulated in Earth system models, it's too conservative compared to observations. And the bottom line is that many limitations in global climate and Earth system models are related to either coarse resolution, inadequate parameterization, underrepresented processes, or limited knowledge of some processes, some physics and interactions. So basically what we've done is that we used an approach similar to the NCAR Community Earth System model, and we basically developed a regional model of the Arctic system, which involves the atmospheric component, the sea ice component, the ocean, the land hydrology. We also have the routing scheme for moving river runoff from land to ocean. And we also have marine biogeochemistry, both in the sea ice and the ocean, but I don't think I'll be able to mention any of this in this talk for 10 minutes. The bottom line is that we have variable model configurations for each component. The default for atmosphere and the land is 50 kilometer, but we're currently testing and running simulations with a 25 kilometer pan-Arctic simulations. Ocean and sea ice is default 1/12 of a degree, which is about 9 kilometer. But we have actually run a lot of simulations, especially forced ice ocean simulations at 148 degree, which is comparable to what Eric Chassinier was talking, and Dmitry, they're running 150th. In the Central Arctic, for rotated coordinate system, we have about 2.4 kilometer resolution. Another important aspect is that we vary also the vertical resolution in the ocean model. Default is 45 levels, but we also have 60 level simulations where the upper 100 meters are resolved at 5 meter layer thickness. Finally, we have variable or alternative rheology for sea ice. The later one, anisotropic, compared to the more traditional isotropic EVP rheology. And finally, the last important part is that we have a very high frequency coupling across different components, which actually allows us to address and resolve some of the processes that are temporally limited if they are not able to resolve them. On the bottom here, I'm showing that we have different model configurations, fully coupled models, which are referred to as RBR, and then forced simulations where the ice and ocean is active and forced with atmospheric analysis such as Core2 or similar. So the first result I wanted to show is a paper by Alice de Vivier from Journal Climate, where looking at the fully coupled model simulations and using self-organizing maps, basically the RASA model results were used to look at the impact of the westerly tip jets from Greenland and their impact on the mixed layer depth in the Imogen Sea and in the Labrador Sea. I don't have time to talk about this, but actually if you do the self-organizing maps, you can have a different patterns of different behavior, and then look at the relations between the characteristics of the westerly tip jets and the mixed layer behavior in a fully coupled sense. So the main message here that I'm trying to pass is that you will not be able to address this particular problem here in the Imogen Sea and the Labrador Sea in terms of the impact of the atmospheric forcing on the mixed layer depth, deep water formation as well, if you don't have the processes represented or required to represent the deepening and mixing within the mixed layer depth, as well as maybe deep water formation as a result of it. Another result, very important one, which is actually related to the temporal coupling, is that if we have a 20-minute resolution temporal coupling across different model component, we can get the inertial peak in the power spectrum of the atmospheric forcing and its impact on the sea ice. So the storm passing through the Arctic, which is highlighted here in the red, and not at the center of the storm, but somewhere out off the line, which is the point here where spectral location calculated is. And you can see that we get the inertial peak on the left panel in terms of the storm passage, and the response in the ice rotor drift spectra represented by the RASM by this light color, and the buoy spectra shown by this darker purple color. So we have a good agreement on that. And I'm not showing those results, but this paper by Roberts et al. Is basically saying that if you don't have the resolution to represent the temporal coupling across different metal components between atmosphere and sea ice in this case, you won't see that power spectrum peak in your RASM or sea ice drift power spectrum. The bottom panels are showing basically an example of what happens when a storm passes across the sea ice in the Western Arctic. So we're looking at the Bering Strait here, the Western Arctic, Chukchi, and the Beaufort Sea. And this is a span of about 7 days between January 20 and 26th of 1980. So it's not the same storm as in the paper here. But the bottom line is that it's showing basically the fragile ice formation as the storm passes in the Western Arctic. And this fragile ice might be actually an important contribution overall to the new sea ice production as well as thickness distribution due to those deformations that are taking place in the Arctic. So in order to represent the storm passing, the ice deformations and the ice production, high resolution is critical. Another important aspect, what we have between the coupled and the force simulation results, the upper panel is showing the time series of sea ice volume with the two coupled model simulations. The blue one is using just standard elastic viscoplastic isotropic rheology, and the black time series is showing the time series of volume for an isotropic rheology, which is the newer one. And basically what you can see here is that it's about 20% of total volume increase in the anisotropic rheology versus the isotropic rheology in a fully coupled simulation, where only rheology is different between those two runs. When you look at the bottom panel here, it's exactly the same set of two experiments, but forced towards reanalysis. So it's ice-ocean force simulation. And the bottom line is that there is an increase in the anisotropic rheology, but roughly half of what's increased in the fully coupled simulation. So the bottom line here is that very important aspect is that when we look at sensitivity of various processes in coupling, we need to recognize that force simulations might not give us the full understanding of the sensitivity when we run a fully coupled simulation with process resolving configurations. One other thing that is important is that the oceanic heat content in the upper ocean is present there throughout the winter. So the upper left panel here showing a time series of the ice setter profile drift in the Western Arctic, shown here on the right. And basically, if you look at the timing here, the red color indicating warmer water about freezing temperature at depth about 40 to 80 meters is present through the winter, January through April, and that water might be actually available to be entrained into the mixed layer to the bottom of the sea ice when we provide some dynamic processes to entrain this water. And one of them could be deformation in sea ice, and the lower left panel is showing the monthly mean, March mean surface total heat flux from the ocean to the atmosphere, where we have repeated deformations occurring in the Western Arctic along the border, or along the border between the fast ice and the pack ice, which is moving with the atmospheric forcing. So the yellow and greenish colors are representing increased surface flux to the atmosphere, which is on the order of about 35 and maybe more watts per square meter in a monthly mean sense during the winter time. When we go to the subarctic North Atlantic, such as the Barents Sea and the Greenland Sea, the blue colors here, again, monthly means for March represent heat fluxes from the surface of the ocean to the atmosphere along the marginalized zone represented by the black contours on the order of 300 or 400 watts per square meter in the monthly mean sense. So bottom line is, again, that if you want to understand the ocean atmosphere coupling in terms of those surface heat fluxes to the atmosphere, we need to have the sea ice as in the subarctic North Atlantic, or we need to have deformations represented as in the Western Arctic to account for this heat source during the winter time from the ocean to the atmosphere. One other important aspect is that the ocean advects heat from the lower latitudes to the Arctic, which was also mentioned by Eric and Dmitry in the first talk. And I'm showing here the 4 panels at the top, where we look at the total heat convergence by the ocean into the Arctic, into the central Arctic. The black lines here, time series, are net input of the heat to the Arctic. So basically we have, in a fully coupled simulation, about 8 terawatts of total heat convergence into the Arctic. It has to be translated to the atmosphere because there's no other way, or to the melting of the sea ice. And we're comparing it to the 4 simulations on the second left panel, the 4 simulations with 9 kilometer and 60 level vertical resolution. And then the last panel on the right at the top is a 2 kilometer 45 level simulation. So basically you can look at those black numbers here that change with the model configuration, forced versus coupled, as well as the vertical and horizontal resolution. And the bottom panels are showing basically the mean sea ice state, partly in response to this oceanic heat convergence into the ocean, into the Arctic. So finally, I wanted to finish up with the predictions. We have contributed the sea ice prediction for the September forecast. Sami Kamal and colleagues have been leading this effort. The upper panels are showing the 2017 initial conditions used for predicting September mean. So this is the early June initial conditions based on the monthly mean of May for 2017 from fully coupled RASM simulations that started in 1979 through 2017. And then we extended through June for a July prediction and for July for August predictions. And the bottom panels are showing our September mean prediction. The purple line contour represents the passive microwave observed mean September 2017 ice extent. So we, as Stephen was talking about the sea ice prediction comparison, our prediction was order of 500,000 kilometers square off. And the bottom line that if you look at the upper panels, actually I believe we have very good initial conditions, but to run the forward simulations for RASM, coupled simulations for RASM, we have to have lateral boundary conditions from elsewhere. And we're using the NCEP CFS V2 forecasts that are available publicly in advance for running our lateral boundary conditions forward simulations for RASM. Finally, I will finish up with just an anecdotal result. Sami ran the simulation starting in September based on the August mean conditions. You can see that actually the comparison with observations, which is purple line, is not perfect. But if you look at the November 28th, 2 days ago, forecast from RASM compared to the purple line here from observations, especially in the Western Arctic, we're doing relatively well. And those discrepancies that we have in the subpolar North Atlantic, I think we have some understanding what they will be related to, in particular to the inflow of warm water across the Barents Sea and the Fram Strait, which might be responsible for excessive ice extent in this region. So finally, in order to increase model resolution in terms of what Eric and Stephen were talking about, we're already running 2 kilometer resolution for sea ice, which is probably already past the threshold of some physical assumptions that are related to treating sea ice as the fluid instead of granular material. So this is a result, preliminary results from a project that is funded by Department of Energy for developing the discrete element model for sea ice. Adrian Turner is a PI and Andrew Roberts a co-PI from MPAS. And basically, this is taking an approach that Mark Hopkins proposed some years ago, 20, 30 years ago, and developing it for the fully coupled simulations pan-Arctic, but also taking advantage of the exascale high-performance computing capability that DOE and DOD as well are very strongly considering for taking advantage of. So I'll finish here, and we'll be happy to take any questions as well. Thank you.